You know that smartphone in your pocket, the one you're probably watching this on? Well, it works because of a truly bizarre set of rules that governs how our universe operates at the absolute smallest scales. Today, we're going to dive headfirst into that strange and wonderful world, quantum mechanics.
So let's start with a pretty wild question. What if the predictable, everyday rules of reality what if they just break when you zoom way, way in? What if, down at the level of a single atom, the universe plays by a completely different, almost nonsensical set of laws?
Because that's exactly what scientists stumbled upon about a century ago. You see, they had this beautiful, elegant system that seemed to explain everything, but it was about to hit a massive wall.
For centuries, classical mechanics was the undisputed king. I mean, from Newton's laws of motion that describe a falling apple to Kepler's laws that map the orbits of planets, these rules just worked perfectly. The universe felt like a giant, predictable clockwork machine.
But then, when physicists finally built instruments sensitive enough to look at the microscopic world, that perfect clockwork just shattered. Classical physics had no answers for why atoms didn't just instantly collapse on themselves or why a heated object glows a very specific color. The old rulebook was failing, and frankly, physics was in a complete crisis.
So, what came out of that crisis was nothing short of a revolution, a totally new instruction manual for reality, with some very, very strange but incredibly powerful new rules.
Okay, rule number one is quantization. Forget what you learned about energy being this smooth, continuous ramp. Nope. At the quantum level, energy is a staircase. An electron can be on step 1 or step 2, but it can never, ever be on step 1.5. Energy comes in these tiny, indivisible packets called quanta.
Now, if you thought that was weird, the next rule is even stranger: wave-particle duality. It turns out that everything, and I mean everything, an electron, a proton, you, me, is both a solid little particle and a spread-out wave at the exact same time. It's just that the smaller and faster something is, the more wavy it starts to behave.
And this weird wave-like nature leads directly to one of the most famous ideas in all of science, Heisenberg's uncertainty principle. What it means is that there's a fundamental limit to what we can even know about the universe. You can know exactly where a particle is, or you can know exactly where it's going, but you can never ever know both at the same time. It's a cosmic trade-off.
And this visualizes that trade-off perfectly. Look at the left side. We see a sharp, narrow spike. That means we know its position very, very precisely. But its wave is all jumbled up, so we have absolutely no clue about its momentum. Now on the right, it's the exact opposite. We have a nice, clean, predictable wave, which tells us its momentum, but now its position is completely smeared out all over the place.
So if we can't know things for certain, how in the world do you do physics? Well, physicists had to make a trade. They gave up certainty, and in its place, they embraced probability, using a really powerful new mathematical tool.
And that tool is called the wave function. It's represented by that Greek letter psi. And you can think of it like this. This single function holds every single thing that can possibly be known about a quantum system. Its energy, its momentum, you name it, all wrapped up in the language of waves.
But here's the real magic trick. The wave function itself doesn't actually tell you where the particle is. Instead, if you take its magnitude and you square it, what you get is the probability of finding that particle at any given point in space. Quantum mechanics doesn't give us concrete answers, it just gives us the odds.
All right, I know this is all pretty abstract, so let's make it real with one of the most famous thought experiments in all of quantum mechanics. Let's see what happens when we try to trap a particle using these new rules.
So picture this. We take a single electron, and we trap it. We put it inside a tiny, one-dimensional box with walls that are completely impenetrable. It can bounce back and forth, but it can never, ever get out. So what do our new quantum rules say is going to happen?
The result is incredible, and it shows the core idea of quantum theory perfectly. Just by confining the particle's wave, we force it into these specific, neat, standing wave patterns. And because of that, its energy becomes quantized. It can have the energy of level 1, or level 2, or level 3, but absolutely nothing in between. The box itself creates the energy staircase. This isn't just a theory, it's a direct result of the wave nature of matter.
Okay, I know. A particle in a box seems very abstract. But what if I told you that this exact principle, these quantized energy levels, is the secret behind pretty much all of modern electronics? Let's see how this little thought experiment builds the phone in your hand. You see, in a real solid material like silicon, you don't just have one atom in a box. You have trillions upon trillions of them all packed together. And their individual, neat little energy levels all start to interact and overlap, and they smear out into these huge, continuous ranges of allowed energies. We call these energy bands.
So just like a single atom has allowed energy levels, a solid has allowed energy bands. But what's really crucial is that there's also a forbidden energy gap between them, a range of energies that no electron in that material is ever allowed to have. And the size of that gap, well, it determines everything.
This one simple concept explains the huge difference between all kinds of materials. In a conductor, like a copper wire, the bands basically overlap. There's no gap, so electrons can just move around freely, and that's what we call electricity. In an insulator, like rubber, that gap is huge, so the electrons are totally stuck. But the magic happens with semiconductors, like silicon. The gap is small, it's just right. You can give the electrons just a tiny little nudge of energy to make them jump that gap, which means you can control the flow of electricity. And that control is the basis for every single computer chip ever made.
So there you have it. The fundamental difference between a copper wire, a silicon chip, and a rubber racer isn't just about what atoms they're made of. It's about the collective quantum behavior of all their electrons, and it's all dictated by the size of that forbidden energy gap. This is quantum mechanics in action, right here.
So, we've kind of come full circle, haven't we? From the moment classical physics completely failed to explain the atom, it was clear that a new framework was needed. And that framework, quantum mechanics, didn't just solve those old puzzles. It gave us the tools to literally build the modern world.
And that leaves us with one final, kind of mind-bending thought. We build our entire world on silicon chips, devices of incredible logic and precision. And yet, their most fundamental operation relies on the quantum rules of pure probability and uncertainty. So if the bedrock of our logical digital world is fundamentally random, what does that really say about the nature of our reality?